Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge, which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicists Podcast, and I'm Ben Tippett. And now, ALLEZ! Physique! One of Carl Sagan's most popular sayings is that extraordinary claims require extraordinary evidence. So, what if someone were to tell you that 70% of the world's food was eaten by ghosts? And then if you ask, well, have you ever seen a ghost eating 70% of the world's food? They'd go, well, no, but they're ghosts. No one's ever seen them eating food because they're ghosts. But the food is missing. This would probably start a pretty incredulous discussion about the evidence which led to the claim. Now, a lot of people have responded, fairly reasonably I think, to the claims that 70% of the mass in the universe is generated by strange, mysterious, invisible type of matter we ominously call dark energy. We've never seen it, but we know it's there. And we know it's huge, and it's massive, and it's ever-present. Today, we're talking about dark energy. You know what else is huge and massive and ever-present? It's Ben Caplan, his beard, his voice, his glasses. Ben Caplan is an indie rock musician, and he's based out of Halifax, and he tours internationally. He sings songs that are rollicking and raucous, and it's like a gypsy pirate music. Oh, wow. Hey, Ben, welcome to the show.
Hello.
So you can find more about him on his website at bencaplan.ca, or you can follow him on Twitter. Go to @BenCaplanMusic, where you can find those links on our website. So Ben's the brother of a good friend of mine, and I've been looking forward to inviting him on the show for a while now. So when I finally got around to introducing myself to him, I asked what he'd like to learn about, and he said, dark energy. So anyway, here we are. So Ben, for you today, I've assembled two fantastic titanium physicists. Arise, Dr. Rupinder Brar. Dr. Rupinder is one of the friendliest people I know. He's so good at making science fun that in 2010, he won TV Ontario's Lecturer of the Year Award. He got his PhD at Queen's University, and he's currently a senior lecturer at the University of Ontario Institute of Technology. Now arise, Vicky Scowcroft. Dr. Vicky got her PhD from Liverpool John Moores in the UK. She's currently a postdoc at Carnegie Observatories, where she works on the Carnegie Hubble problem. She even has a new knitting podcast called One Starry Knit. We'll have a link to it on our website as well if you want to find it. All right, let's start talking about dark energy.
Let's put the problem in context. Let's start in the early 1900s. So it's almost like the debate that's going on right now happened in a sort of different way about 100 years ago. 100 years ago, theoretical physicists were debating, is the universe itself static, like non-changing, infinite, or is it something that changes with time? And basically, we were able to solve this question through one of the greatest observational astronomers of all time, Edwin Hubble. And basically what Edwin Hubble did was he measured the distances and what we call redshifts of galaxies. And basically redshift just means that he's able to figure out how fast these galaxies are going. So these are distant galaxies. He can now measure their distances, but also not only how fast they're going, which direction they're going. And the big discovery was that all distant galaxies are moving away from us. And essentially what this showed was, in fact, that the universe itself is expanding. So we're living in an expanding universe where essentially space itself, the distance between distant objects, is getting larger and larger. And I mean, this is the universe that I grew up in, right? This is the universe that we were raised on. And it sort of sets the picture for what comes next.
So what's the relationship between Hubble and Doppler? It's called the Doppler effect, right?
That's absolutely right. So this idea of redshift is just another way of saying the Doppler effect, right? And so light coming from distant objects is going to be what we call either red-shifted or blue-shifted through the Doppler process. And so if it's coming towards us, it's going to be blue-shifted. If it's going away from us, it's going to be red-shifted. And so if you imagine a universe of randomness, of non-changingness, pretty much half of the galaxies should be moving towards us and half of the galaxies should be moving away from us. So you got to imagine the surprise or the shock, really, of when Hubble did this experiment 100 years ago and figured out that all galaxies, other than the few that are really, really close to us that are gravitationally interacting with the Milky Way, but all other galaxies are moving away from us. The only explanation could be that, in fact, the universe itself is expanding. So there are other possible explanations, but the thing is, the further the galaxy is, the faster it's going. That's the key. So the further you are away from us, the faster you're moving away from us. And that definitely translates into an expanding universe.
Beautiful.
Have you ever heard of Einstein calling something his biggest blunder?
I haven't heard about that.
Okay, so there's a story. So this whole red shifting, blue shifting, Doppler shifting thing is interesting because mathematically redshift isn't a Doppler shift. It's an analog to Doppler shifts. Doppler shifts happen in sound. Red shifting and blue shifting happens to the color of light. So something that puts out white light, if it's moving away from you really quickly, that white light will be shifted and we'll see it as red light, just like how the pitch changes in Doppler shifting. So we usually explain red shifting and blue shifting processes in terms of Doppler shift analogs. But all this Doppler shifting comes from Einstein. Like, he was the guy who predicted it when he invented special relativity. So in 1916, Einstein produced his theory of general relativity. And it's the theory of gravity. So it's the theory that talks about black holes, and it also talks about the universe expanding. And the thing about Einstein's theory of gravity is that it imagines that everything in the universe lives on it's kind of like it's a four-dimensional sheet called space-time. You've probably heard of the space-time continuum. That's what they're referring to. So right after the First World War-ish, people were playing with different models for gravity. So one of the models they came up with is essentially the black hole solution. And another model has some very simple assumptions built into it. So you face these equations and you say, how am I going to simplify these equations and come up with a model? And the simplifying assumptions were pretty neat. They said, okay, so what if everywhere in the universe is like everywhere else? It's called the Copernican assumption. It's based off Copernicus. Copernicus was the guy who said, what if the sun doesn't go around the Earth? What if there's nothing special about the Earth and everything in the solar system going around the sun? So Copernicus was like, there's nothing special about the Earth. And so this Copernican principle says, well, what if there's nothing special about anywhere? What if everywhere is essentially the same? And it's a lovely set of assumptions because the equations become very simple. And what it ends up describing is a universe that's expanding or contracting, but this contraction or expansion happens everywhere at the same time. So it's kind of like anywhere you go in the universe, you'll see the universe expanding in the same way. So there's no center of attraction. It's not like an explosion where everything explodes out from a single point. Instead, it's kind of like, we often describe it in terms of, so if you take ants and put them on the surface of the balloon and then start inflating the balloon, the distances on the balloon will start increasing, but technically speaking, there's no center on the balloon that everything is being attracted or repelled from.
Mm-hmm. And the ants don't get any bigger.
The ants don't get any bigger.
Right.
So
the form space.
That's right. So Rupinder was saying people at this time were really conflicted because, philosophy had been around for several thousands of years, and what philosophers decided was that the universe should either exist forever or maybe God built the universe at some time, but there's no reason the universe should have a beginning or an end or anything like that.
And interestingly enough, I think Einstein was part of that school too.
Yeah, that's right. So Einstein bought into this, and he looked at his equations, and his equations said the universe can either be shrinking or it can be expanding. And it can't do neither. It can't just sit still. And so Einstein said, well, let me add a term here. And he added this term called the cosmological constant to it, which is it's a constant that you stamp into the equations. And what the constant does is it has the capacity to make space-time solutions that don't expand or contract, that just stay the same.
Does the constant have a physical relationship or conceptual relationship to any force or any ratio within the universe?
That's a good question. So at the time it didn't. At the time, he just inserted it by hand. And mathematically, since then, people have justified him doing so. So we think that it's not mathematically flawed to add a constant where he did, but he did it because he wanted a cosmology that didn't change.
So he figured out how to solve the equation to exactly what he wanted it to.
Yeah, but he had to add a little term in there to his original equations. So since then, mathematicians have said, oh, maybe that constant should be in the equation, but Einstein just put it in because he found it aesthetically appealing, right? The solution he got from it. But then immediately after that, Hubble came out with his finding that said, oh, hey, look, the universe is expanding, which is what Einstein's theory originally predicted. Which is why he said, oh, this is my biggest blunder. Why did I go out on a limb and say that there was this constant that had everything still? I'm so wrong, right?
One more thing we should mention about the Hubble observation before we go on to this new dark energy observation is that finding the velocity of these distant galaxies is actually really easy. The hard part is finding the distances. The distances to faraway objects is one of the most challenging things in observational astronomy. And the only reason he was able to do it was because of this type of star called a Cepheid variable star. And so a Cepheid variable star is a specific star that basically gets brighter and less bright, brighter and less bright very, very regularly. And the period of that brightening and dimming is directly related to its actual luminosity, that is, its intrinsic brightness. And so by basically measuring the period, you know how bright that star is. And by comparing how bright it actually is to how bright it looks through your telescope, you can use that relationship to figure out distances. And that's what Hubble did, and there's a variation on...
It's what we still do today. Like, this is what I do all day. Like, we're using exactly the same technique that he used 100 years ago, because it's still the easiest way to do it. It's still hard, but it's still the easiest way to do these things.
What is it that's causing the change in luminosity of the star?
So it's got helium in the atmosphere of the star, and as it gets hotter, the heat can knock off electrons and ionize the helium, but that changes the chemistry inside the star, so the radiation starts to get trapped. So as it gets trapped, it makes the pressure go up, which then pushes the star out and makes it get bigger, and that changes the brightness. But then eventually it goes too far, and then it cools down because it's got bigger, and then it starts to shrink back in on itself. And it just keeps doing that and doing that. But it's really regular because it's basically just like a sound wave propagating through this star. So you can predict it really simply what it's going to do.
Would you describe it as in light frequencies?
Yeah, we use period or frequency. We tend to use period because the period is typically a few days. But there's another type of star that we use for distances of closer by things where the period is a few hours. But the Cephids are what we use for the nearby and quite far away galaxies.
So what is the process of using the change in the light? It's still a bit unclear to me. The way in which the light changes, how does that allow you to pinpoint the distance? How do you transform that period into a measurement of space? From
the period and from what we already know about these types of stars, we can work out how bright it really is. And then you take an image of the star and measure how bright it looks to you. And then you take the difference of those two numbers. So it's if you had a 100-watt light bulb and I held it right in front of your face, you would be blind. And also it would be really bright. But if I moved it to the other side of the room, it would look fainter. And you know that the amount it gets fainter is proportional to how far away it is. So you can work out by how much fainter it looks how far away it is.
Yeah, at first I thought that, you were using the change in the light to determine what the true brightness is, but you're using a calculation based on the period of the light to figure out the true luminosity, not by direct observation, but through calculation of the change.
So we have a relationship. There's like a well-defined relationship between the period of the change and how bright the star really is. So we have a few stars that are nearby that we can directly measure the distance of by seeing how they move. But with parallax, like when you close one eye and then close the other eye, things tend to move. We do the same thing with these stars using observations in January and July or whatever. So we do the same things with the ones that are really close and then use that to calibrate out to get further and further out.
When you say January and July, you're measuring the parallax by using our knowledge of where the Earth is in relation to the sun, and then taking as wide a point as possible to triangulate the distance?
Yeah, that's exactly it.
And so basically for the next 100 years, until 1998, we're living in a universe that we know is expanding. So basically what scientists are trying to figure out now for the next 100 years is what's eventually going to happen to our universe. Are we living in a universe that will collapse back on itself in this sort of big crunch? Will the expansion reverse? Will it sort of come to some beautiful equilibrium and just stop? Or will it expand forever but sort of slow down as it goes? And the answer to that is no.
I'm not clear. What was the no to? The no is that it can't expand forever?
No on all of those. All three of those turned out to not be valid, in fact, due to these brand new observations that we'll talk about.
Yeah, so there was three. It could either expand for a while and then run out of energy and then collapse back in. Or it could just keep expanding and then eventually slow down and then just carry on going, but a really slow rate, or it could just keep going forever and kind of Okay, so they wanted to look at these different types of expansion. So they looked at stars called supernova, which are kind of like the Cepheids. So we know exactly what brightness they should be. So if we observe them, we can work out how far away they are. So they were looking at really distant supernova, as far away as we could observe. And they found that these supernova all look too faint from what you would expect them to be. So that either means that there's something wrong with our supernova model, or the supernova are further away than we're expecting them to be. So there were two groups that discovered the same result at the same time. And for a little while, neither of them published because they were both we must have messed something up here. This is just insane. And then eventually both of them did publish it. And then they realized they were both seeing the same thing, but from different observations.
And the reason they're afraid to publish is because they're afraid that the findings are challenging the present model, which is highly problematic?
No, it wasn't that. It was they weren't sure if they were right. They wanted to be really sure that they were right. Once they'd convinced themselves of this, then they did publish. So they published this saying that the supernova was too faint. And then the explanation for that is that the expansion of the universe is actually accelerating. So it's not just that the things further away from us are moving faster, they're getting faster and faster all the time as you get further and further away.
So right after the Big Bang, the universe was expanding. The space-time itself had a kind of momentum that was pulling all the objects in the universe apart. It was adding volume to itself. It was getting bigger and bigger like the surface of a balloon. And what happens is, before this discovery Vicky was talking about, we expected that initial momentum to be essentially all the universe had driving the expansion, right? We know based on what Hubble discovered that the universe is expanding currently, and then we expected the matter in the universe to kind of slow the expansion of the universe down. So in this case, there are three possibilities. One of them is that it keeps on expanding forever, just like, you know how the Earth has an escape velocity? So if I take a ball and I throw it faster than the escape velocity, the ball will keep on going forever?
Yep, that's rockets get up into the sky.
That's right. We kind of imagine the universe doing that. It was possible if the universe had enough velocity right at the get-go that all of the deceleration caused by the gravitational attraction of all the dust and planets and stars in the universe would cause the universe to slow down, but it could be that the initial velocity of the universe was so fast that it blew past that limitation and we'd just keep expanding forever, and then we'd have nothing. Everything would be so diffuse, the universe would be empty. And another model said that we would have less than the escape velocity of the universe, and the pull of gravity would cause the universe to recollapse. It's expanding right now, but maybe in a few million years it would begin recollapsing down in on itself and you get a big crunch. Now, this discovery Vicky was talking about said that the universe isn't decelerating the way we would expect it to decelerate from the attraction of all the objects in it. It's accelerating. So things aren't just getting farther apart, they're getting farther and faster and faster.
Whew. I mean, I guess that means that the analog of throwing a ball and being able to predict what it's going to happen falls apart because there's apparently more and more complex forces at work than we had initially anticipated.
It's kind of like the ball was actually a rocket, and after it left its hand...
No one knew the ball had a rocket built in.
Yeah.
Yeah, what's the evidence that everything is accelerating? And how recent has that been confirmed by observation?
So the original evidence from the supernova was in 1998. And the people who discovered that actually won the Nobel Prize like 2 years ago. But it's been confirmed in other ways now. There's a satellite called Planck, which has just released its results recently. And that was one of the ones that's confirmed it. And what it does, it measures all like the radiation left over from the Big Bang, called the cosmic microwave background. And it measures like the sizes of all the fluctuations in the background. But what it does is it measures all the sizes of these different fluctuations and measures how many of each one there are. And from that, it can work out what the universe is made of, like how much of it is dark matter and how much of it is regular matter and how much of it is dark energy. And they work out that like 70% of the universe must be dark energy. And you're like, well, why would it be that? But if you take that like with the supernovas as well, and you say, well, how much dark energy must there be in the universe for those supernovas to look like they do? It's 70% as well. So now we have two different things that are saying like that 70% of the universe was eaten by ghosts.
So is this 70%, is it based on sort of observation? And dark matter is, can we say that it's analogous to a vacuum, or is it something radically different than the absence of matter?
So dark matter it's just like regular matter, but we can't see it. So it behaves like gravitationally in the same way.
There's two things at play here. So when everybody made their ridiculous announcements, they said that there was dramatic evidence for two things that we can't see: dark matter and dark energy. So dark matter is a type of matter. So it's like planets that aren't shiny count as dark matter. And so what you can do is you look at galaxies, and galaxies are rotating. So everything in a galaxy is swirling like stuff around a drain. And the thing that makes our sun orbit the galaxy is essentially the gravity of everything inside its orbit. All that matter. So you can figure out, based on looking at how fast all of the stars are as you move from the center of the galaxy out to the edge, you can figure out how much mass is contained as you move from the inside to the outside of the galaxy. And you find that there's way more matter in a galaxy in terms of the velocity that things are orbiting than there is stars. And so you say, all the other stuff that must be there, but isn't shining like a star, we'll call that dark matter. So we've known about the existence of dark matter for a while now, but in addition to it, all of these cosmological dynamics tests that Vicky was talking about confirm the existence of dark matter. So now we have two big demonstrations that dark matter exists. But in addition to that, there's this weird dark energy thing, and nobody knows what causes that.
Some of the names are unfortunate. Dark matter, dark energy. The reason we call them these things is because we have no idea what they are. That's really what it comes down to. There's no relationship.
You replace dark with mysterious.
Yeah.
We call it dark because everything we do in astronomy is looking at light. Because we can't go out there. Like, we use a telescope to look at the light, and this is something we can't see, so it must be dark. That's it. That's as simple.
So go on. Tell me more about how dark energy relates to the problem of accelerating the universe.
Okay, so it's like this. When you're talking about the dynamics of the universe as it expands, the deal is that the more concentrated the matter is, the more potent it is gravitationally. So most matter, like your beard, if you stretch out your beard, it becomes more diffuse, right? Its density decreases. So usually what would happen is, as the universe expands, normal matter, like the distribution of galaxies, becomes more diffuse. So the overall effect of the matter becomes less potent on how the universe evolves, right? So to make the universe accelerate, what you need is a special type of matter, because if the universe is accelerating, it means that whatever's driving that acceleration is getting more and more potent.
I see.
So somehow, the larger the universe gets, the more of this dark energy there has to be.
So let's say a sandbox had a certain amount of sand in it.
Yeah.
And the walls were movable, but then the sand would become, less voluminous. There'd be less density of sand within the sandbox, and we would expect it to slow down. But instead, it's like more sand is just appearing out of nowhere that continues to push the sandbox wider.
That's exactly what it's like.
Yes.
Very good.
Great.
Let's suppose you had a box that was empty. It had nothing in it, vacuum.
Yeah.
And you doubled the size of the box. Would the density of the vacuum increase or decrease?
Well, I suppose if it's a vacuum, it's already by nature not possible that it increase or decrease. It's already nothing.
Very good. I mean, it's just as nothing as it was before. It's just like you said. So the deal is that one of the possible candidates is a type of energy. It's a type of gravitational effect that's constant. It's like the vacuum. It's ever-present. It's everywhere. And so, just like the vacuum, if you double the size of the universe, it will keep the density the same. Just like that. So, there's one thing that works just like that. And we talked about it already. It was called Einstein's biggest blunder. That constant that he added into his equations in order to make the universe stand still, you could choose a constant for that constant that makes the universe expand and accelerate. And it's called the cosmological constant, and it's one of the candidates for why the universe is accelerating. So the deal is that it's not becoming more potent as the universe accelerates. It's just as potent throughout its life. But the thing about the cosmological constant is all of the rest of the matter in the universe is getting more and more diffuse. So in comparison to the regular matter, the cosmological constant, if that's what's causing the expansion, gets more and more dominant over the regular matter. And so it's driving the accelerating expansion. So in the end, it might have been Einstein's greatest move ever in that he predicted this thing 100 years earlier, except that nobody knows if that's it.
This cosmological constant that's now driving the bus, as it were, is there any sort of analogy of how it exists spatially or temporally within the universe?
So there's two different explanations, depending on whether you're coming from my point of view, which is just a parameter. So the way I would imagine it is all gravity is caused by curvature. So what we call gravity is actually the effect of curvature on space-time. So in my picture, the cosmological constant, it's kind of like, imagine you were trying to tile a basement. You were trying to build something out of a bunch of tiles. You opened up your box of tiles, and each of them was kind of smushed. You know, they're still rectangular, but they're kind of curved like Pringles. You can make them meet edge to edge, but if you did it so, you would end up with a large, weird, curved shape instead of a nice flat shape. So in essence, the way I understand this cosmological constant is it's kind of like that. It's kind of a four-dimensional space-time curvature that each of the points in the space-time kind of has, just like each of these tiles do. So your space-time inherently has a curve to it, and that curve is being exposed as the matter becomes more and more diffuse. But there's another that people explain this curvature, and it's through something called vacuum energy. You ever heard of vacuum energy before?
Never heard of vacuum energy.
In quantum mechanics, all systems are imagined kind of like guitar strings. And what they say is, they talk about exciting a system, the way you excite a guitar string by plucking it. And they say at the smallest levels, things are quantified. You can only add very discrete packets of energy to it. It's like saying that a guitar string can oscillate at 1 decibel or 1.5 decibels, but it can't oscillate at 1.4 decibels. There's no intermediate states. So then the mathematics of quantum mechanics say that at its lowest state, once you've extracted all the possible energy out of an object, it's still got a little bit of vibration to it.
Because the lowest possible state is not zero.
Yeah, so effectively, you treat it like it's a vacuum. It's got no more energy to give, so in some sense it's a vacuum. On the other hand, it's got a little bit of energy to it. So quantum mechanics, as it started, was very well behaved, and before too long, people started applying quantum mechanics to more than just particles. We started talking about quantum mechanics about electromagnetic fields, these larger systems. And what happens is if you break down these more universal fields in terms of quantum mechanics, you see these vacuum energies popping up. There are times when, an electromagnetic field will have no excited state. There won't be any photons in it, but it will still have some inherent energy to it.
So even though it seems like the field is not active or present in any way, it still acts.
Yeah, and the thing is, when you add that to gravity, you'll say, okay, each of those little motes of vacuum energy are going to add up, and that means that the field will have some mass. And when you add up that mass, you usually get infinity. So they do a couple tricks with the math to get not infinity. Though, they can predict how much mass this vacuum energy is going to have. And then they can compare the predicted theoretical vacuum energy mass to the measured vacuum energy mass. And it is 120 orders of magnitude too high. It's some people call it the worst prediction from science ever.
So, not off, but way up.
Yeah.
Gotcha.
This is called the cosmological constant problem. And nobody knows how to resolve it.
We have an issue.
Nobody knows whether that vacuum energy is gravitating or whether it's just a thing that lives in the mathematics. Nobody knows if it might exist, but somehow there's some other secret field that's canceling out the energy so that you end up with a fairly low number. So nobody knows whether this prediction is true or not, but it's possible. This vacuum energy might be the thing that's driving the accelerated expansion of the universe.
The worst problem is it's the same problem we have with of dark matter. We can infer that dark energy is there because we see its effect. And we can infer that dark matter is there because it messes up what galaxies look like. But we can't find it. We can't go out and get some or say, oh, this is a dark matter particle or this is what dark energy is. We're still guessing right now.
So it seems as though the visible forces of the universe are nested somehow inside invisible forces that we can't really see.
Yeah, for us to have the universe that we observe to be consistent with the theories that we have, you need a whole bunch of invisible players behind the scene pushing things around.
And to be honest, I think the theoreticians are definitely behind here. No offense, Ben. We've
done our job, so
yeah, we've given a couple of possibilities and stuff. But the real answer as to what dark energy is probably, I don't think we've come up with it yet. And one thing that maybe we'll mention just briefly, since we have been talking about dark matter as well, is there's always sort of the concept that maybe something we do know about, we just don't know about to the proper degree. Like, say, the concept of gravity or general relativity. Could there be something more complex about it, that when we get to larger and larger scales, we honestly just don't have a proper theory for how gravity or general relativity works. And that's how the properties that we now call dark matter and maybe eventually call dark energy, could those be described by a more complete theory of gravity? I'm not proposing that that's true, but it's certainly something that smart people are thinking about.
So one of the interesting things that's come out recently with Planck is that, so they measure the fraction of dark energy and dark matter and regular matter and other things like the rate of expansion of the universe in one way. They measure it with the microwave background. And there's another group of people, including me, who measure it by measuring distances to very nearby galaxies instead of the really far away microwave background. And we get different answers. So right now, we have no idea why we get different answers. So it's entirely possible that there's something we just don't quite get yet. So it's an exciting thing to work on because we have no idea what we're doing. It's great.
Sounds so exciting.
It's kind of frustrating. I think it's frustrating because, Rupinder said that there's a whole bunch of alternative explanations, and there are, but the problem is that we don't know enough. We're getting enough information that we know that the universe, as we understood it back in Hubble and Einstein's time, isn't right. We know that the universe is accelerating, and we know how much it's accelerating by. We know a few more parameters, but there aren't all that many. And so what happens is you can make a lot of different theories of gravity that account for the differences. Technically speaking, adding a cosmological constant to Einstein's theory of gravity is technically a different type of gravity. It's a matter of, it's really an academic thing. It's like arguing whether Han Solo shot first. It's because it's so trivial and because Einstein added the term on his own. But people do much more ridiculous things. Some people are arguing that Einstein's theory of gravity should have additional terms, where Einstein's theory of gravity is just a simplest approximation to how the universe really works, and that curvature should play a much higher role in affecting matter. And nobody knows whether that's true or not, but people are playing with it. They're called F of R theories of gravity. They're really neat. Some of them predict the dark matter. Some of them account for mass having a bigger vote the farther away you get from it, which would account for why galaxies spiral the way they do. Others of them predict accelerating expansion like our universe, and it's lots of fun.
So, it seems like physics right now, to me it sounds analogous to the state of astronomy or the 15th, 16th century, where you're adding circles upon circles upon circles. Each orbit has another orbit, and you're tinkering with this model of the solar system until it's so insanely complex and ugly. And so we've got these models where we're adding rules and adding formulas and different principles and different ways of looking at things and bringing new things into the model. With Galileo, the move is to a more beautiful, easier to understand model that is radically different and has different underlying principles at its core. Mm-hmm. So perhaps dark energy situation predicts that a new model, and I guess a unified theory, would replace the old model entirely.
Yeah, that's certainly possible.
Yeah.
For sure.
It's exactly like that. We've got a theory that doesn't fit. Einstein's original theory of gravity doesn't fit. We know that a small tweak that's mathematically correct can allow for the universe to increase in size the same way. But just like when we saw the stars doing their retrograde motion and we couldn't predict it, and astronomers started adding these circles, we don't know which theory is right. And you can modify the theory. You can make new theories that all predict the same type of expansion.
The retrograde motion was, the models were insanely complex,
yes.
but they actually were perspective.
Yeah, but maybe we really just need to switch around the way we're thinking about it.
Yeah, that's right. So, I mean, right now there's a plethora of explanations. They do all sorts of things. It's actually fantastic. It's like a golden age for theory because there's enough data to justify changing the orthodox theory, but not enough data to choose which of these potential candidates for the successor is the correct one.
But what needs to happen in any sort of scientific method, right, is going to be for these new theories to make predictions for the observers now. We need the theoreticians and the computational physicists and all these guys to be all like, look, if this specific theory is correct, then you should be able to observe this specific thing. And then we'll go out there and we'll see if we do see it. That's the only way we're going to progress in this different scenario.
One of the things to remember about this is easy to forget, like dark energy, that was 1998. That was less than 20 years ago, and we've come all this way in just this short amount of time. But what we need to do now is we have the satellite experiments measure one set of parameters, and when they measure these numbers, they can't always disentangle them. They're measuring one thing, but it's kind of linked to another number, and they're not getting a unique answer. So you need different types of experiment to be able to say that we can definitely split up these values and we can measure how much dark energy is and completely disconnect that from a different parameter about the universe. And right now we can't do that. So we have to think of different ways to look at it. Hopefully we'll get there soon. But
one of the things that theorists do on Theorist End, we don't just dream up new theories, but one of the things we spend a lot of fun time doing is when somebody proposes a new theory, it's usually fairly simple. They say, hey, why don't we just do this? And they'll add a new term and they'll throw something up and we'll say, oh, okay, is that right? In addition to looking for things we can test, just like Rupinder says, one thing theorists do is we look for inconsistencies. And so one of the problems with various modified gravity theories is they'll explain dark matter, but they can't explain dark energy. Or alternatively, you can tune them to explain dark energy, but they won't be able to explain dark matter. So it's a pretty fun time these days because there's lots and lots and lots of explanations for why the universe is expanding the way it is, but we're not sure which is right. We're in the Wild West.
I'm going to stop playing music and start studying physics.
Well, if you want to, you're welcome.
Come and join us.
Yeah.
This music thing, I mean, I don't know. It's not nearly as exciting as all this physics.
Well, I don't know. You're pretty good at it.
Maybe I'll keep up with what I'm doing. But it's fascinating. It's an exciting time.
So thank you, Rupinder. Thank you, Vicky. That was great. You've pleased me very much. Your efforts have borne fruit, and that fruit is fruit. Here is some fruit. Vicky, you get a pear. And Rupinder, here is a mango for you. All right. I'd like to thank my guest, Ben Caplan, the clever indie rocker with the beard that just won't quit. More information is on his website at bencaplan.ca, and if you want to follow him at Twitter, go to @BenCaplanMusic. Thanks, Ben.
Thank you.
Did you have fun?
I sure did, Ben.
Hooray! So, my TIE Fighters, listen, I love this show, and I hope you do too. But for every listener to the show, I know that there are 100 other people who would love to listen to the show, but they just don't know how. So I want you to spread the word. And there are 3 ways you can do this. The first is iTunes. It's still the biggest place to go find new podcasts. So most frequently rated shows are at the front, where everybody can see them. So if you've got a minute, give us an iTunes review. It'll increase our rank and more people will see us. The second is to teach people how to listen to podcasts, which is funny, but everybody you know has a smartphone or a tablet these days. And a very low percentage of these people know how to listen to podcasts. So if you know somebody who'd like to listen to the show, ask them if they know how to listen to podcasts. And if they don't, point them to the Stitcher app. And I don't say this lightly, but the Stitcher app is useful. It's easy to use, and it works on almost every handheld device. So whether they're working with an Apple or a BlackBerry, they can still listen to Stitcher. So you do it, your grandmother will thank you for it. And the third way to talk about a show is to tell people online about us. The internet is full of explanations about physics. If you see someone on the internet talking about a topic one of our episodes covered, or maybe a news story, post a comment at the bottom telling them about the show. All right, that's it. I hope you'll help us out and point new listeners in our direction, so thanks. So that's it for the main part of the show. Remember, if you'd like to listen to scientists talk about science in their own words, you might also want to listen to our other shows on the Brachylope Media Network, like the Weekly Wienersmith, where Kelly and Zach Wienersmith talk to academics about their research, or Science Sort of, where we talk about science and science in the news. So editing support for the Titanium Physicist podcast is provided by a gentleman named John Heath. Thanks, John. You're the reason we sound so good lately. The intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Until next time, my friends, good day, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
Right? Okay.
But then you would expect the vacuum itself to limit the size of the container.
Oh, yeah. Well, if you're in the atmosphere, you're pulling against the atmosphere, and then you need really big arms, like a musician's arms. Yeah. So you're right. But
in space, it wouldn't worry about that.
Yeah, it's in space. Playing the accordion is very easy. Yeah.
Yeah.
Right, because there's no vacuum, there's no pressure on the outside of the vacuum that limits the vacuum.
That's right.
Yeah, so you're just making your box twice as big and still having...
So space-time is curved in the way I understand it, and then everything in space-time. If you imagine like three kids in the space in a skateboard park, okay, and they're all on their skateboards, and they're standing right next to each other in a line, and they all kind of what's the verb for scooting on your skateboard?
Skating.
They all start skating in one direction. So there's three of them side by side, but then skate parks usually have bumps and curvature to them, and so it won't be long before all three of them are moving on entirely different trajectories. One might be going up, and the other might be going to the left, and the other one might be going to the right, and they'll skew their directions. So effectively, that's what we interpret as gravity. When we say gravity causes matter to collapse, what we're actually describing is how the curvature of space-time messes up with the trajectory of all the objects in the universe. It kind of skews things. There's another way to make dark energy, though. Have you ever heard of a big rip?
No.
The characteristic of this dark energy is it's something that doesn't get less potent the more you stretch it out.
Mm-hmm.
A cosmological constant, it would stay the same. No matter how much you stretch it, it's like a box with nothing in it. You can make the box bigger. The amount of nothing hasn't increased. But you can invent other types of theoretical matter that get more gravitationally potent the more you stretch them out.
So it's almost as though there's a kind of anti-gravity. The laws of gravity are reversed.
Well, yeah, kind of. It's the laws of conservation of matter, kind of, that are reversed. It's kind of negative accounting. If you imagine your sandbox example, you stretch your sandbox to twice the size, and suddenly there's 4 times the sand that was in it before. And the sand gets denser and denser the bigger your thing increases. It's very weird stuff. Now, if the universe has stuff like this in it, it's called phantom energy, right? If you stretch out this phantom energy, it gets denser and denser the more you stretch it. And what this will cause is the universe will get bigger and get more dense, and get even bigger and get more dense, and get even bigger and get more dense. And the more dense it gets, the faster it gets bigger. And so it will cause a runaway expansion of the universe. So the universe will start expanding faster and faster and faster. And we can talk about physics in terms of domains, because we know that if you're really large, if you're the size of groups of galaxies, you'll feel the tug of the universe expanding. Mm-hmm. But at solar system level, we can't feel the tug of the universe expanding on us. The force of gravity by the sun, the electromagnetic force of the atoms binding our skin together are all much stronger than the force of gravity of the universe expanding. So it's negligible on Earth. But the thing is, if you get this weird runaway expansion, the force of expansion everywhere in the universe will get stronger and stronger and stronger. Suddenly maybe the tug of the sun on Pluto won't be enough to hold it in its orbit because the acceleration of gravity will be too fast. And then maybe as the universe gets faster and more dense with this phantom energy, the sun on Jupiter won't be strong enough to hold Jupiter in its orbit anymore because the universe is pulling out on Jupiter so hard.
So if the universe keeps expanding, the whole universe will just basically get ripped apart by this force as it continues to accelerate.
That's right, and it will accelerate all into a point, so it won't happen gradually. It'll zoom in. All of a sudden, suddenly the stars will blink out, and then we'll lose all the planets, and then the sun will go dark as the Earth is pulled away from the sun, and then we'll get pulled off the Earth, and then our bodies will get ripped apart. It's called a big rip because it rips everything apart.
Let me ask you a question then. How does this expansion and increase in velocity, I guess, how does that all relate to the speed of light? I would think that the speed of light would be the fastest that these forces could travel at, but I guess not, or does the speed of light itself increase?
Well, that's a good question. So the speed of light is constant. Let's imagine a balloon. And there's a guy under the balloon blowing air into the balloon. So the balloon is steadily increasing in size. And instead of the speed of light, we'll talk about the speed of ants. So you have ants, and let's suppose that ants all move at 1 centimeter per second. They're kind of speedy ants. So the deal is that, let's suppose you have 2 ants, one at the equator of the balloon and one at the top of the balloon. The ant on the equator wants to walk to the North Pole. There are occasions where the guy blowing air into the balloon is blowing air fast enough, the surface of the balloon will be expanding so fast that even though the ant's moving fast on the surface of the balloon, he'll never make it to the North Pole because the distance between him and the North Pole will be increasing faster than he can cross that distance.
So the medium that light is moving across may be expanding at a faster rate than the light is traveling.
That's right.
But that has no impact on the speed of light itself.
That's right, yeah. So to talk about ants very briefly, what you can do is, if you know how fast the balloon is expanding, you can draw a circle around the North Pole, or any point on the balloon, in fact, and say, ants that are farther away from the North Pole than that circle will never be able to reach the North Pole because of the expansion of the balloon. Similarly, you can say that in our universe today, because we know how it's expanding, we can say that there's a distance away from us where anybody past that distance will never be able to communicate with us because the distance between us is increasing faster than light can cross it.
So, even in the whole time of the universe's existence, there won't have been enough time for that light to travel across there.
Yeah, well, given an infinite amount of time, it will still never be able to make it. It's kind of like Lucille Ball on the assembly line. She can't eat the chocolates fast enough. They're piling up. So this is called a cosmological horizon, incidentally, and it's kind of like the Earth is in a black hole. We can't communicate with anybody past this distance. It's really, really large. But the deal is that the faster the universe increases in size, the smaller that cosmological horizon gets. So if the universe is expanding really, really, really fast, we might not be able to communicate with Andromeda anymore. So in this big rip scenario, what happens is we imagine that circle getting smaller and smaller and smaller and smaller as the accelerating expansion of the universe gets faster and faster until your legs can't communicate with your head because the distance between them is increasing too fast.